Today's lecture is about terrestrial laser scanning, or we call it ground-based laser scanning. Depending on the platform you used for laser scanner, we have airborne based laser scanning, or we call the airborne LiDAR, or even space-based or satellite-based laser scanning. But today's lecture will focus on the ground-based or terrestrial laser scanning. Okay, so the objectives of today's lecture is to understand the basic principle of terrestrial laser scanning. The next one is the categories of a terrestrial laser scanner. So what kind of laser scanners you can say, okay, especially used in survey or spatial area. And we know the terrestrial laser scanner is not only used in survey, okay, it has been used in a wide range of application area. But probably, and as a survey student, certainly, okay, we will focus on the application in survey and the spatial area. Okay. The next one is to explain the error sources in terrestrial laser scanning. Okay, for any survey tasks or survey instrument we use, we have to understand the possible error sources that could occur, and or any potential effects to your final result. So we have to understand the error sources, and then if we can, we take some measures to minimize the effects of the error sources on your final result. Okay. The next one is to understand the general procedure of a laser scanning survey, include some application example. So what's the terrestrial laser scanning technology? Is active remote sensing technology. It's not passive, because laser scanner will send a laser beam to the target you are interested in, okay, and then receive this retained laser signal. In this way, we can determine the point position in three-dimensional space. But not just one point or single point. We have to use the rotation, okay, rotate the instrument around the vertical and the horizontal axis. So simultaneously, we can get thousands laser retained point. Can collect a huge amount of point in three-dimensional point. High density, high accuracy, three-dimensional point. These figures show you the basic principles of a terrestrial laser scanner. Okay, you can say the laser come from here and meet with a rotating mirror. So this one got this mirror got a 45 degree to the laser beam, and then can deflect this laser beam 90 degree from here to the target. Okay, we use, if we rotate the instrument along the vertical axis, and at the same time, we also use this rotating mirror, okay, to rotate along this horizontal axis, so we can get the laser scanning, laser returning point, okay, from different direction, different area. The ranges we can get from 1 meter to 1 kilometer, or even to several kilometers, okay, depending on the laser scanner you use. And you will see this, okay, in the categories of terrestrial laser scanner, you will see this different laser scanner got different scanning range. Advantages: collect a huge number of points, high density, high accuracy in a short period of time for 3D modeling, mainly used for 3D modeling, but certainly can also be used for other area. The basic formulas of terrestrial laser scanner quite similar to the EDM. Okay, we measure distance, and through this, by this formula, you can say if we can measure the time laser beam travel from instrument to the object and then return back to the instrument. If we certainly will know the velocity of the laser beam. Okay, travel from the travel speed or velocity, and then we can calculate the range. But don't forget divide by 2, because you measure the time that's travel from the instrument to the object and then back to the instrument. Okay. The previous example, the formula is calculated in the vacuum medium or in the vacuum condition, and but the laser beam travel in the air. Okay, air is medium. So we, from the survey A or from any other courses for the EDM, we know the laser beam travel in the air will be affected by the temperature, pressure, and the humidity. So that means we have to consider the effects of refractive index. What's the refractive index? It's a value, or it's a ratio between the velocity in the vacuum and in the air. Okay. So we got a value very close to 1, but always greater than 1. That means in the air, laser beam always travel with a little bit slower speed compared to the vacuum. Okay, so if we consider the refractive index, the range value can be calculated by this. Okay, if you can get the time, okay, laser beam travel. Scanning mechanism, this show in this figure. Okay, you see laser beam come from here and meet a mirror, and then this mirror rotate along this horizontal axis and deflect the laser beam 90 degrees to the target or to the object. Okay, and at the same time, okay, return the laser beam and then to the detector. So record the position. Okay. We have different mechanism to deflect the laser beam. Okay, the first one we call the panorama scanning mechanism. This one, panorama, is actually the one we already know from the previous slide. Okay, used by the ferro laser scanner. Laser beam and deflected by this rotating mirror, okay, to the target and then back to the detector. Okay, so quite commonly used deflection unit. So other deflection, the beam deflection unit, you can say the first one is this one, the oscillating mirror. This one is used by Leica Scan Station 2, for example. Okay, we use this Leica Scan Station 2 in our teaching 10 years ago in USQ. That's also the first laser scanner in USQ. It's used a deflection method this way. Okay, oscillating mirror. So it's a mirror just move like this, and if the instrument can at the same time, okay, rotate around the vertical axis, so you can get the returning beam from target. Okay, quite commonly used, probably also used by other laser scanners. Okay, and this one, rotating polygon. The polygon, if you see from one side, is actually like this. Okay, so this way, and deflect the laser beam to the target. And also this one we call the fiber scanner. So first, deflect the laser beam to this optical fiber. Okay, and then throw this fiber pointed to the laser beam to the target. The last two deflection unit or deflection method quite commonly used in the airborne LiDAR. Okay, this one and the rotating mirror or the panorama deflection unit are the ones used by the terrestrial laser scanner. This one, some of these, okay, some of the laser scanner also use this rotating polygon. This one is mainly used by the airborne LiDAR because that's complicated. You can say that it include the optical fiber. Okay. Directly collected data is the point data. Okay, in three-dimensional space. That means you can represent your point data in a coordinate x, y, z, or easting, northing. Okay, if you after you transform your laser scanning point from one coordinate system to the other. But directly, the point represented in a local station coordinate. The origin or the center of this kind of a local coordinate system that's in the point when laser beam meet the rotating mirror. That's the 0 point. So you got the 0, 0, 0 position. And then from here you will say, okay, the vertical axis and the x and the y. So because we can measure this angle, vertical angle, horizontal angle, so certainly we can calculate this point x, y, z. But remember that's in the local stations coordinate system. Okay. Categories of laser scanning. So what kind of laser scanner or what kind of laser scanning technology we can use in different laser scanners? The first one is pulse-based, or in the term of laser scanning technology, we call the time of flight method. So we directly measure time, laser beam travel from instrument to the object and then back to instrument. But this way is from your study, okay, for the EDM, we know this kind of technology cannot get a very high accuracy time measurement. So the second way, we directly measure the phase shift. Okay, laser beam travel from the instrument. Okay, they got an initial frequency phase. When retain the laser beam back to the instrument, there will be something change in the phase angle or frequency, and so we call the frequency shift. Okay. And we measure this, we measure frequency shift, indirectly measure the travel time. Okay, but in this way we can increase the time measurement accuracy. Okay, up to 100 times. So currently for the laser scanner, we can see you will see some example shortly, okay, in the following slide. The pulse-based or the time of flight based technology and used by some kind of laser scanner. And then the next one, phase-based. Okay, in USQ, we got time of flight laser scanner and also phase-based laser scanner. The first one is time of flight laser scanner, Leica Scan Station 2. Okay, the second one, phase-based, is a Faro laser scanner. Okay, so you will say what's the difference, what's the advantages and disadvantages for different laser scanners. Okay, the next one is the triangulation-based measurement. Specifically designed the laser scanner use a triangulation-based measurement. Okay, it's not commonly used in survey area because of the short distance. Okay, or the short range. You will see this, okay, in the following slide. Let's have a look first the pulse-based or time of flight laser scanner. This one directly measures time, and the advantages of this is longer range, 1 kilometer up to 1 kilometer or even several kilometers from instrument to the object, scanning object or the object you are interested in. Okay. The drawback for this is you got a relatively low scanning speed. You only got probably around 50,000 points per second. Okay, so mainly used for the environmental application. In survey area, in open cut mining industrial, that's very good. Okay, because we need a long range. Okay. This picture shows you some examples of time of flight laser scanner. The picture doesn't include all this kind of laser scanner, but give you some typical laser scanner and some of these commonly used in survey area. Okay, the first one is Optec. This one is the Leica Scan Station 2 in USQ. Okay, we still, that's the first laser scanner we got in USQ. You will see this one, there's no interface for operation. You have to use a laptop, use a cable or wireless connector to this laser scanner. So all your operation are from the laptop. Okay, there are two windows. This one we call the major laser beam window. Okay, suggest the limitation area this. If you want to scan this on the top, you have to use the second scanning window. Okay, complicated. This one is Regal. Regal is commonly used, okay, in Australia. For example, in Queensland Government Remote Sensing Center, they use this kind of laser scanner for the forest scanning. Quite different design. You can see this one is a digital SLR that's mounted on the top of this laser scanner. And all this one, laser scanner got an internal high-resolution digital camera. Okay, but the Regals, you have to use an external digital camera. Okay, so before or after scanning, you can take photo to the scanning object to help you for the point classification or segmentation or even for the 3D modeling, something like this, okay. And this one is a Trimble. Yeah, I can't remember what's this one, okay. And this one is quite commonly used in mine survey in Australia. ISIGHT, time of flight-based laser scanner, you can see so big and also quite heavy, more than 10 or 20, maybe 20 kilogram. But very reliable, very strong, so suitable for use in the mine industry. Okay. The next one is a phase-based laser scanner. Advantages of this, we can get a high-speed scanning. So that means in a very short time we can get more point data. For example, okay, for phase-based laser scanner we can say, and they can collect point up to 1 million points per second. But the disadvantages of this kind of laser scanner usually got a short range, okay, and around or less than 100 meter. Okay, just 100 meter, not 1 kilometer. So mainly used for 3D building modeling, or for the indoor scanning, or the short range. Okay, for underground mining, that's okay. Usually with a short range. Okay. Now let's have a look at the principle of phase-based laser scanner. We already know we don't directly measure the travel time. We measure the phase shift. In this way, indirectly measure the traveling time. Okay, so the formula is like this, and the time we can calculate it. You measure the phase shift, delta phi. Okay, this one is the wavelength, modulation wavelength, and this one is the velocity of the laser beam. Okay, n is the number, the integer number of the whole wavelength. Okay, we rearrange this or rewrite this formula, and we can get okay, and derive the formula like this from here. Okay, so that means we can remove this C. Okay, and then rearrange this to get this. Okay, and further rewrite this formula. We can represent this formula like this, okay, in the format like this. We call U is the unit length. Okay, it's a half of the wavelength, we call the unit length. In here, we call this ambiguity interval. Ambiguity interval. We rearrange this, we call this called unit length, or we call the ambiguity interval. We call this one, we call the ambiguity number. Okay, ambiguity number, and this one is the ambiguity interval. This one is the phase shift we can measure. So the only thing we can measure is here. Okay, the difference of frequency. And this one we know. Okay, once you determine or you know from the laser beam frequency used in the laser scanner, that's modulation wave frequency, not the carrier wave. Okay, so the only thing we can measure is this one. This one we call the ambiguity number. We don't know. Like we use steel tape to measure distance. We measure 3 or 5 times for the whole length of steel tape, but we forgot how many numbers we measured. Okay, it's 3 or 5. So this one we call the ambiguity number. It's similar like this. We don't know how many the whole wavelength. Okay, from the instrument center to the object. We don't know. In GPS, we also got this kind of a problem. We call the ambiguity. Okay, but we use a different method to solve this kind of a problem. For example, in GPS, GPS phase observation, we use what we use. We use differencing technology. Okay, or plus other algorithm to solve the ambiguity problem. But here, if we can get this n, that's fine, but no way to get this n. So can we take a different ways to avoid measure this? Okay, so the following slide will show the principles for this. Okay, used in EDM and also in the laser scanner. Okay, and we can also use the L to represent this. Okay, the fraction of the unit length. So then finally, the formula is simplified to this. Ambiguity number unit length plus this the fraction of unit length. Okay. So can we take measure, okay, to ignore this or to avoid the measure this ambiguity number? Okay, now we use this figure to show this. Okay, we use multiple modulation wave. So you can see this one, okay, that's the carrier wave frequency. And we have two modulation wavelengths. This one, the low frequency or the long wavelength. The second modulation wave is this high frequency and short wavelength. Okay, so one carrier wave with two modulation wave. One is high frequency and the second one is the low frequency. So the coarse range, that's the coarse range, determined by the low frequency, that's the longer wavelength. And the high frequency modulation wave to determine the accurate range. What's that mean? So let's have a look at the example of this. These examples include one carrier wave and two modulation waveform. This one is the high frequency or the shorter wavelength modulation wave. Okay, and from the formula, we know the L is it's like this. Okay, that means we time the partial of a frequency shift time to the unit length, and then we got this part. Okay, so that's this formula tell you. And this one we can get from your measurement. And then time this, we get the fraction of unit length L. So this one is the L, okay, show here. That's from the high frequency or the short wavelength, we got this. So then we use low frequency or longer wavelengths to measure this phase frequency shift, and then time by the unit length. Okay, longer wavelength, and then we got the fraction of unit length. So then we combine this together. So then we got the final. Okay, so in this way, we didn't measure this ambiguity number. Okay, so the final formula from the previous slide we already know. Okay, the range is like this. Ambiguity number from this example, you can see actually we didn't measure this. we just use this. That's from here. We only consider this, but from two different modulation waves. The coarse range from the low frequency modulation wave. The accurate part of the range was measured from the high frequency modulation wave. Combined this fraction of the unit length, and then we got the final result for this. Okay, the EDM is actually used the same principle for this. Okay, so in this way we avoid directly measure the ambiguity number. I can tell you, and 2 or 3 decades ago, we actually used the EDM to measure distance 10 kilometers and 20 kilometers. Okay, so this kind of EDM, they use more than 2 modulation wave, 4 or even 5, because a longer range, you use just 2 modulation wave, you cannot get this final solution. There will be some gaps here. So they increase the number of modulation waveform. Use 4 modulation waveform are quite common, and maybe 5 possible. Okay, you can imagine this, but not for GPS. GPS is too far away. We cannot use the different the modulation wavelengths. Okay, to throw the combination and to get the solution for ambiguity number. No. Okay, so we use a different technology. Hopefully, okay, this one probably the most difficult things from today's lecture. Okay, hopefully give you some idea. Okay, how can we get this? But remember, we still call this a single laser frequency laser scanner. Why? Single frequency, that means just one carry wave. But we got some modulated signal, like GPS. Okay, we got single frequency, dual frequency back to this case. One carry wave, 2 modulation waveform. Okay, so still single frequency laser scanner. But we do have a dual frequency laser scanner or multiple frequency laser scanner currently. Okay. This picture shows you the examples of phase-based laser scanner. The first one, Faro. Faro laser scanner, and you can see use panorama laser beam deflection mirror. Okay, so 45 degree to this laser beam direction, and then deflect the laser beam 90 degree. Okay, point to the target. And this one is the Leica phase-based scanner. Okay, next one, EyeSight, phase-based, smaller. Okay, much more smaller. Remember the last one for the time of flight laser scanner I show you. That's the EyeSight. EyeSight time of flight so big. Okay, this one is a phase-based from same manufacturer but phase-based. This one just 5 kilogram. Much smaller, and also you can see there's a touchable screen here. You don't need a connector to a laptop, but if you like, and certainly you can through a wireless, even use your smartphone to control the operation of this laser scanner. Quickly have a look at this. Triangulation-based scanning. There's a laser unit, okay, send the laser beam to the target, and then we got a laser detector, or sometimes this one called camera, so return the laser beam. So in the instrument, we got a short constant distance, so we call the baseline. That means that this one always got a constant distance value. And then we can measure these angles, alpha, beta. So in this triangle, we can calculate this range from instrument to the object at very high accuracy. If you can measure this angle, it's actually not difficult to measure these two angles at a very high accuracy. But the problem is, with the increase of the range between instrument and the target, you calculate that the accuracy of this range will decrease. Okay, because the triangle will become very narrow. Okay, as a surveyor, we know this one is not a good geometric shape. Okay, so we usually limit the range for this kind of laser scanner just less than 10 meters. Okay, so that's certainly you can imagine that for survey area, this cannot be a commonly used laser scanner. Okay, but for industrial equipment check, quality check, okay, it's very good because can get a very high accuracy scanning result. Okay. Anyway, other laser scanner. This one is Australia CSIRO designed laser scanner, mainly used for the forest canopy scanning and to calculate leaf area index in the ecological area or the forest modeling or for the carbon biomass estimation. Something like this, okay, and got still hold the patent. And 5 or 7 years ago, okay, and other laser scanner, this one, based on the CSIRO's design idea and also the patent, okay, so they designed their own laser scanner. Also used in the forest area. This one designed by Alan Strela, okay, in the Boston University, USA. This one by the Mark Denson from Salford University, Manchester, UK, and this one from another university in Boston. And all these three laser scanners use dual frequency. That means they can just one scanning, they got more information. Okay, they even can use multiple frequency, try to get information about the forest leaves humidity or something like this. Okay, and but you cannot say cannot get the laser scanner, this kind of laser scanner from the commercial market. Okay, still used in the research area. Error sources in terrestrial laser scanner. Do you want a break or just continue finish this and then we have a break and before we go to the computer lab? Okay, good. Okay, the accuracy of the scanning point from laser scanner certainly is affected by several error sources. But mainly we can group them in the three different categories. The first one, instrument errors, okay, caused by the laser scanner. Second one, depending on the surface reflectivity, or the surface material, or the characteristics. And the last one is the environmental error, temperature, pressure, something like this. And from the EDM principle, you know, and the temperature pressure will affect the distance measurement accuracy. Same thing here. Now let's have a look at this. Okay, the first one, instrument error. The range uncertainty, but certainly the will related to the range or the distance between instrument and the target. So usually about the range measurement accuracy, we can say usually is a 5 millimeter to 5 centimeter. Okay, within this range. If the range is less than 50 meter. So longer distance certainly will increase the error, decrease the range measurement accuracy. Angular uncertainty or angular measure error caused by the vertical axis, horizontal axis, and the collimation axis error certainly okay will also reflected into the scanning result. Laser beam divergence, edge effects are the other two factors affect the laser scanning accuracy. This small picture show you if a laser beam arrive to the target or the scanning object like this, that certainly will create some kind of error, okay, because it's very hard, okay, to ask an instrument, so depending on instrument to determine the range, okay, in this situation, from there or from there. Certainly in the laser scanner, there are some kind of the filter or the algorithm you can use, you can select, okay, so increase the quality, for example. Okay, so use the internal or onboard algorithm, increase the scanning time, and then calculate a best range for this. Okay. Surface reflectivity. Certainly different object surface will also affect reflected laser signals accuracy. White surface, usually you can get a very strong reflection. The black or the dark surface certainly okay will produce a weak reflection. So that's why in the laser scanner or even in the airborne LiDAR, we certainly directly you get a three-dimensional point data, but at the same time you can also get intensity data that reflect the returning signal's strength or how strong your reflected laser beam, something like this. That's certainly mainly related to the surface material. Okay, but how about the color material? If the object surface is different color, okay, that's also depending on the spectral characteristics of the laser beam. Okay. And for some very special object surface, for example, if it's a mirror and initial, okay, thinking, and we say, oh, that's probably a very good reflective material or the surface, but it's not. For mirror, you will got some kind of this speckle noise. Because if this is a mirror, okay, the laser come here, that will 100% to reflect all the laser beam to another object, for example. If this one is an object, and then that will reflect like this way. Okay. So probably you cannot get any retained, or maybe some kind of, but not directly from this the object surface. So usually the object surface, okay, for laser beam, that's reflected like this. Okay, so the laser beam come here, and that's like this. So we receive some of this, not all of this. But for mirror, that's different. Okay, that's reflected all the things. Okay, so that's not good. So we'll cause this kind of noise. Okay, too strong, not good. Temperature. The instrument temperature and also the object surface also affect the scanning accuracy. Atmosphere. That will affect the refraction index. Okay, we know this from the EDM principle. We know, okay, the temperature even and other the factors will affect this refraction index. So that one certainly will affect the range measurement accuracy. Okay. Interference from other radiation sources. Okay. And we use a laser beam, certainly that could be affected by other radiation sources. Okay. Distortion from motion. If you use a scanning station, okay, and at a long time, okay, both the target or the object you are scanning and also the instrument could got some movement. Okay, that certainly will affect your scanning result. General procedure for laser scanning survey. Usually, okay, like any other survey tasks, include this, okay, and preparation for the scanning survey. So we have to know the objective of this laser scanning task. What's the requirement from your customer? Okay, just for detailed survey, for 3D building modeling, or for any other purpose. Okay. The next one, performing the scanning survey. So after you determine the objective of this laser scanning survey, and then you can select the suitable laser scanner, longer range time of flight, or the short range phase-based laser scanner. Okay, depending on your scanning task. Process the scanning data, and then prepare the final product or the deliverables. So depending on the objectives of your scanning task, you know, okay, what's the final product. It's just a cleaned point cloud or 3D model or other product. Okay, so the first on the customer's need or the objectives are very important. Okay, and then you can determine the goals and the objective from scanning survey, and also related product. Search for required information. For example, if your final product need, you put the laser scanning data in a specific coordinate systems. You probably need to search for some permanent control mark or the existing control marks and the related coordinates. Okay, for georeference. Or you maybe use get equipment, extra equipment, for example, GPS receiver or total station, in order to get some control marks position. Okay, for the purpose of georeference. The next one is determine the scan station, determine the location of scan station, and also the location of target. We need a target. Okay. If you have done the practice 3 practice in laser scanning, and you already know this, okay, why do we need put some scanning target? quickly have a look at this. Okay, scan station, and for the same scanning object, okay, this building, we got. You can set your instrument, okay, in a different location. So for this, for example, in these two pictures, you say the first one, you set the instrument very close to the building. The second one, you set your instrument a little bit away from the scanning object, this building. Okay, which one is better? The second one is better than the first one because you can say that the instant angle is very good. This one you got very small instant laser instant angle. Okay, so that will affect the scanning accuracy. This slide show you the target location, possible target location. Again, we can say for the same scanning object, we put target in these two pictures in different location. Okay, distributed quite differently. The first one, we put nearly all the target at the height level just above the ground level. And also the range are quite similar. This one, we put target at a different height level, different elevation, and also we put this one at least one target, okay, not along this building surface. Okay, so certainly the second picture show a good location for the target. Okay, evenly distributed with different height, even different range. When you study the photogrammetry and the remote sensing course, you know, okay, for the also rectification, we need a GCP or ground control point evenly distributed, and then you can get a very good result for the also rectification. Okay, so same thing for this. Otherwise, if you use the first situation, that will affect your registration purpose, or even sometimes you fail your automatic registration. Target. What kind of target we can use in the laser scanner? Generally, we can use either the natural targets or the artificial targets. Okay, what are nature's targets? We can say, for example, in this classroom, okay, then you can say the many different planes, corners. All this one we can treat them as natural targets. Okay, for the indoor scanning, that's okay. Okay, we can locate so many corner nature target to use for your automatic registration or manual registration. That's okay. But for the area outside this building, probably not good. Okay, so many thousands of corners the software can recognize, or it's for some features they are not a corner. For example, the forest or the tree leaves, and for one leaf they can detect several corners, small corners. Okay, so that's not good. Okay, so anyway, so usually we use some kind of artificial targets as shown here. And different manufacturers use or provide a different target. Checkerboard, sphere, and also other target. Okay, this one, and for example, can be used for Leica scan station tool. These two, certainly checkerboard can also is used by the Leica scan station tool, or can be used by most of the laser scanner. And the sphere firstly provided by the Faro scanner. Okay, Faro scanner use stage 1. Why use stage 1? For sphere, okay, and no matter where you set your station, from any direction, you can always see a circle. Okay, compared to this checkboard, just from a single plane, that's not good. Okay, if you set your instrument with a very small instant angle, you probably, okay, the software probably cannot automatically recognize the center of this checkboard target. Scanning operation. Set up the instrument on the top of tripod or the camera tripod, and then put some target. Okay, that's the basic setting up for the instrument and for target. How many targets we need? Minimum 3. But usually we put more than 3 targets, 4 or 5, just in case during your scanning, one target move, or you didn't get enough number of returning point from 1 or 2 target, you still got a minimum requirement 3 target for the registration process. Okay, otherwise, if you only got 2 target, you cannot finish the registration. Okay, what's the registration purpose? We want to combine the laser scanning come from different laser scan station. You will see this in more detail in the following slide. In order to get enough returning point from the target, you cannot set up or put your target too far away from laser scanner. Little bit more detail, you will see this in the following slide. That's also depending on the different settings. For example, how dense was the density of the scanning point and how big the scanning target you use. Okay, that will affect the distance between target and the instrument. Use this example as a dialog window or the interface from Faro laser scanner to give you some idea how can we set up the resolution and the scanning range or the scanning view. So from here you say that we can change the setting up for resolution or for the scanning area. Okay, when you click this button or this arrow, you will see this interface. Different laser scanner probably got different, certainly, okay, got different interface. This one just from Faro laser scanner, okay, the resolution, and you can drag this sliding bar up to increase the resolution or increase the density of your scanning point or increase the quality. And then based on your setting and also related to the scanning area, so that you will see some indication value here in the middle column. So roughly how long it will take to finish the scanning from this point. That's certainly related to the resolution quality and also the scanning area. Okay, so you change any one of these, that will affect this value. Okay, you can say that finish this scan station, you will got 11 million 0.3 points. The point interval is around 12 millimeter at 10 meter from instrument. Although we got a very narrow beam, a laser beam, but with the increase of the range you measured, this point interval may increase. Okay. The next one is set the range, okay, and for most of the instrument, horizontally we can scan 360 degree. Okay, there's no limitation for the horizontal range. Then mainly there's a limitation for the vertical scanning. Okay, different laser scanner got a different scanning default setting for the vertical scanning area. Okay, you can change this setting. For example, I don't want to scan all the 360 degree horizontally, so you can change this one and by press this or increase one by one. Okay, 1 degree by 1 degree, or you can press that one to get a keyboard available on the screen, so you can enter a scanning range. And other advanced setting I want to mention is here. Okay, for example, the clear contour. Okay, that's this edge laser footprint or laser beam get this, and we turn this filter on. Okay, to help the software to determine a better range. Clear sky. Turn this filter on. That means okay, a very good or very clear sky. The instrument can treat this very clear sky as a mirror. So sometimes you will got some funny returning point we call the no object returning point. So we use this filter or turn this filter on. So 95% we can remove this kind of no object returning point. Okay. Different instrument again, and use a different or include different extra this kind of filter or algorithm to ensure the scanning quality. After you finish the field work, upload your scanning data to the software. Usually the manufacturer will provide some kind of pre-processing software. It's mainly for the scanning point registration, georeference, or for with a very limited number or limited functions for 3D model, something like this, but mainly for the registration, georeference, or any other pre-processing. Cannot do a complicated modeling task. Okay, this one, when you upload the scanning point, this example is from 4 scan station. You can see the relatively location between this scanning point not right. Okay, not good. So certainly, okay, they just randomly put them together. So then through the registration and the georeference, okay, working on your copy of your data, not on the original data. Okay, so through registration, we can combine them, combine the scanning point from different scan station together. Through georeference, we put your scanning data in a specific coordinate system. Sometimes we first do registration first, and then if necessary, we did the georeference. We do georeference again. Okay, second step. But sometimes we can do registration and the georeference together. Okay, so after this, we combine the scanning data from different locations, scan stations together, and also put them into a specific coordinate system, for example, MGA94 or other the coordinate system you want. This figure shows you the registration process, okay, and we got 1, 2, 3 scan station, and we use some common target A, B, C, D. So then through registration, we can combine the scanning data together from 3 scan stations. But After registration, you just combine them together, and in a local coordinate, what's the local coordinate system? It's just the software select a reference scan station. Use this reference scan station's local coordinate as the local coordinate system. Okay. Then if we know the coordinates for some target or even for some scan station, so then we can do a georeference. By the end of a georeference, we put them in a specific coordinate system. Okay. This picture shows you the example after registration, and where the color information comes from. From the photo. Okay, so before or after scanning, the instrument usually use the internal digital camera to take photos. That will help you to recognize the different point from different scanning object. Okay, for example, from here, we can easily see or recognize, okay, some point from brick wall, some from the window glass, some from tree or other plant, okay, or from ground. So anyway, and during the registration, if you like, you can select I want to extract the color information from digital photo, and then apply this color information to the individual scanning point. But certainly that will take extra time. But once you've done this, that will help you for the following processing, for example, classification or modeling. Okay, compared to the black, white, or the gray scanning point. This one is a cleaned point cloud after registration. Okay, so remember, only clean your point data after you do registration or possible georeference. Otherwise, if you delete the point from target, you cannot do the registration. Okay, so first the registration and possible georeference, and then clean your point data. Create a cleaned point cloud. Okay, depending on the customer requirement, the cleaned point cloud data may be your final product. Or, if required, you have to use a 3D model or 3D model method based on or use a third-party software to further process your scanning data. Today's tutorial, I'll show a little bit, okay, and how can we export the scanning point data and then imported this to a third-party software. Okay, in practice 3 laser scanning workshop, you already done the registration and create a cleaned point cloud data, I remember. But we just stopped there, and so today's tutorial will show you and how can we export this cleaned point data and then import it to other software, okay, for further processing your scanning data. Finally, we quickly have a look at some kind of applications from laser scanning point cloud data. Okay, the first one, this one is from one of my final year project students. Use our Leica scan station tool. He spent 2.5 days for the field work. Remember, the Leica Scan Station 2 is a time of flight based laser scanner. So relatively low scanning speed. Okay, so that's why he spent 2.5 days around this building, engineering building, and probably I remember there's 13 or 15 stations, include 3 on the top of this building, and the rest of this just a station on the ground around this building. And he also used a GPS receiver to collect the point for some station and a target location. So he then did the registration and the georeference together. Why? Because you can see just the registration cannot combine the scanning from top of this building to the ground scanning data. Okay, so that's why I use a GPS positioning for the georeference. Okay, and did the georeference and the registration together. And then, okay, clean the point data, this one, and then to the segmented point, and then use software and third-party software to create a 3D building model and visualized in the Google Earth. Okay, other examples, application examples, you can see this one is also from one of my final year project students. He works in the mine industry, open cut area, use the eyesight laser scanner. That's a time of flight. Remember from that picture, that's the last one, okay, but quite commonly used in Australia mine industrial. It's an open cut. Longer range, certainly we need a longer range. Okay, 100 meters we cannot, okay, you set up here, probably we cannot get the longer scanning range. Okay. Underground mine industry. Underground. This one also eyesight, but it's a face-based laser scanner. But it's good enough for because for underground mine industrial, you can say, okay, that's a short range, that's good enough. Okay, and it's easy to carry to the underground. Okay, compared to that time of flight laser scanner. And other applications are for the industrial equipment supply. That's the high density laser scanning point. Okay, we want to monitor this or to get the as-built industrial equipment, so we can use laser scanning. Other applications for deformation monitoring is hydroelectric dam deformation. Okay, with the pressure of water. Okay, and so certainly this dam will change. Okay. We've got some kind of deformation. So deformation monitoring, so it's very important. In the past, we can use a GPS receiver or the total station, okay, to monitor this, but it's just for some specific point or the monitor point. But use a laser scanner, you can see we can get a detailed 3D model for this hydroelectric dam, okay. And next one is the heritage protection, and this one is castle, and the next one is a very high density laser scanning point. Okay, to monitor is protected target. Okay, tree and forest structure modeling is another major application area. Okay, this is not certainly not in the survey area. For the research scientists in the ecology or the forest area. The next one is the building information modeling. Each year we got some students from our survey students, survey or spatial science students, or even from civil engineering students. They use a laser scanner, but focus on different objective. okay, for either cadastral, 3D cadastral application or for any other BIM application. Okay, so depending on your knowledge area or your subject area, and do different applications. That's all for today's lecture. Thank you for your attention. We have a break.